Hello everyone, welcome to the next video on Digital Electronics Lab. In this video, we will study about the design and setup of a full adder circuit using XOR gates and AND gates and using NAND gates only, and we'll implement it using the Proteus software. So first we'll move on to the theory part. So as you all know, this full adder is developed for the addition of two 1-bit numbers A and B and a carry in Cn, or it is used for adding three single bit numbers. So it is having three inputs A, B and carry in and two outputs, that is the sum and carry out. This is the truth table of the full adder circuit, and we have simplified and obtained the expressions for output, sum and carry, and we have got expression for sum as A bar B bar C in, or A bar B C in bar, or A B C in, or A B bar C in bar, and the expression for carry out as A B or B C in or A C in. And on further simplification, we can write the expression like this, that is the expression for sum can be written as A XOR B XOR C in, and the expression for carry can be written as A B or A XOR B and C in. So we'll see how to design this using XOR gate and AND gates. So this is the design using XOR gate and AND gate. So the expression for sum is A XOR B XOR C in. So here at the output of the first XOR gate we'll get A XOR B, and at the output of the second XOR gate we'll get this is A XOR B and this is C in. So at the output sum will be equal to A XOR B XOR C in, and the carry out is A XOR B into C in or AB. So this is AB, and this is given as input to an OR gate, and this A XOR B into C in is also given to another AND gate. So the C out will be equal to A XOR B C in or AB. So we can implement this circuit in Proteus software. So this is using XOR gate and AND gates only. Now next is we have to implement it using NAND gates only. So in order to implement that using NAND gates alone, we know the expression for sum. It is like this. So this is an SOP expression. So we can realize this using basic gates alone. After realizing using basic gates, we can replace all the basic gates with NAND gates. So that is this figure. So instead of showing NOT gate over here, we can give NAND gate here. We can show NAND gate here, since this is the realization using NAND gates alone. So this NAND gate will be acting as the inverter. And the expression for carry is, this is not sum, this is the expression for carry. So the expression for carry is AB or BC or AC. So that can be realized using NAND gates like this. So we will implement this also in Proteus software. Now let us do the implementation of full adder using XOR gates and AND gates. So for that we need XOR gate, AND gate, then LED and logic toggle. So I have picked all the components necessary. So first we can take the logic toggle. I'm giving it over here. Then that is A. Here it is B. So right clicking, edit properties A, and here right clicking, edit properties, I'm naming it as B. So now we can take an XOR gate. We can place the XOR gate over here, and we can connect A and B to the XOR gate. Then this output can be given to another XOR gate, and we need an AND gate over here. So the input of the AND gate is A and B. Now we need another input, which is Cn. So I'm taking a logic toggle and I'm giving that over here, and I'm naming it as C. So the input of this XOR gate is A XOR B and Cn. So I'm giving A XOR B here and Cn from here. So the output will be equal to A XOR B XOR Cn. Now the carry out. So for that I have to give another AND gate. So I'm placing that AND gate over here. So the input to this AND gate is A XOR B and Cn. So I'm taking Cn from here and I'm connecting that over here. And A XOR B. So this is A XOR B. So the input of this AND gate is A XOR B and Cn. Now I have to give an OR gate here, and the input of this OR gate is A XOR B Cn, that is the output of this AND gate, and AB. AB is here. So I have to give AB also. So A XOR B Cn or AB. So that is the output of the OR gate, that is the carry out. Now I can connect LEDs at the output. And also I am connecting another LED over here. So this is the sum and this is the carry out. And we have to give the ground also. So the circuit is now complete. Now let us do the run the simulation. So here I am giving 0. So 0, 0, 0. The truth table is over here. So I am naming this also. Edit properties. I am naming it as sum. And I am naming this as carry out. So now let us run the simulation. So for corresponding to 0, 0, 0, sum is 0 and carry out is 0. For 0, 0, 1, the sum is 1 and carry out is 0, that you can see here. For 0, 1, 0, 0, 1, 0, corresponding to 0, 1, 0, sum is 1 and carry out is 0. So sum is 1 and carry out is 0. For next is 0, 1, 1, corresponding to 0, 1, 1, sum is 0 and carry out is 1. Next is 1, 0, 0. So for 1, 0, 0, sum is 1 and carry out is 0. And for 1, 0, 1, for 1, 0, 1, sum is 0 and carry out is 1. So that is carry out is 1 here. So next is 1, 1, 0. So for 1, 1, 0, sum is 0 and carry out is 1. And for 1, 1, 1, both sum and carry outs are 1. So we have verified the truth table. So now let us implement the sum circuit using NAND gates only. So for that we need a 3 input NAND gate and a 4 input NAND gate. The 3 input AND gate is 7410 IC and the 4 input NAND gate is IC number 7420. So I have selected that too. Now let us start doing the implementation part. So first I am taking the logic toggle. So this is for A and let this be for B and the next one for C. So the first term is A bar, B, C in bar. So let us take a 2 input NAND gate and we have to invert A. So I am using this NAND gate as an inverter. So if this is A, at the output we'll get A bar and next we need C in bar. So I am giving another NAND gate and I am Shorting the inputs, and I'm connecting C. So let us name ABC first. This is A, this is C, and this is B. Okay, so we can connect a 3 input NAND gate over here. And we can connect A bar, B and C in bar as the inputs of this 3 input NAND gate. So this is A bar, this is B, and this is C in bar. Next is we want A bar, B bar, C in. So we can take another 3 input NAND gate and place that over here. So here we need A bar. Next is B bar. So we can take a 2 input NAND gate here. Short the inputs and connect B here. So at the output we'll get B bar. Next is C in. So connected C in also. Now I'm taking another 3 input NAND gate. So the input to this is A, B bar, C in bar. So A is here. So A is here. This is A. Next is B bar. So B bar is here. And finally C in bar. So we can take C in bar from here. So now we need one more 3 input NAND gate. So 7410. I'm placing that over here. The input to that is A, B and C. So A is over here. So I'm connecting A here. Next B. I'm taking B from here. And finally C. So I have connected C first. This is actually B and I have to take A. So this is A. So I have connected that too. So this is, as you can see, this is A. And this one is C. And this one is B. Okay. So we can connect a 4 input NAND gate also over here. That is 7420. I connected the 4 input NAND gate here. Now we can connect the output of this 4 NAND gates as the input to this. Now I'm going to give LED at the output. and I'm going to give ground also. So now circuit is complete. Let us do the implementation part. So for that, run the simulation. Then first all the inputs are 0. The expression for sum is 0. Output sum is 0. Next 0 0 1, sum is 1. Next is 0 1 0, corresponding to 0 1 0, sum is 1. So 0 1 0, the sum is 1. So for 0, next is 0 1 1, corresponding to 0 1 1, the sum is 0. Next is 1 0 0. So for 1 0 0, the sum is 1. Next is 1 0 1, corresponding to 1 0 1, the sum is 0. Next is 1 1 0, the sum is 0. And finally 1 1 1, the sum is 1. So we have verified the sum expression. Next we are going to implement carry using NAND gates only. So for that we need 3 2-input NAND gates and 1 3-input NAND gate. So in the component mode, so we first will take the logic toggle. So A, this corresponds to B, and let this corresponds to C. So edit properties, A, this is B, and finally this is C. So first we can take a 2-input NAND gate. So I'm connecting that over here. So the first expression is AB. So I'm connecting A, and next is we are connecting B here. So that is the input to this NAND gate. Next is BC. So we are going to take another NAND gate and we are going to connect B and C to this NAND gate. So this is B and this is C. Next is we have to connect A and C to another NAND gate. So this is A and this is C. This outputs can be connected to a 3-input NAND gate. Sorry, I have taken a 2-input NAND gate. So 3-input NAND gate is 7410. So let us connect this outputs as input to this NAND gate. Now at the output we have to connect LED and also the ground in the terminals mode. Let's select the ground and connect that also. So now the circuit is complete. Let us verify it. So for that, run the simulation. So I have played the simulation, run the simulation. Now for corresponding to 0 0 0, the carry out is 0. Corresponding to 0 0 1, the carry out is 0. Corresponding to 0 1 0, the carry out is 0. Corresponding to 0 1 1, the carry out, as you can see here, it is 1. Next is corresponding to 1 0 0, the carry out is 0. Next is corresponding to 1 0 1, the carry out is 1. Next corresponding to 1 1 0, carry out is 1, and corresponding to 1 1 1 also, the carry out is 1. So we have verified the carry out expression also.